All right, we're going to try to finish up the exam from spring semester. This is this past spring semester's exam. We did 4 problems on Monday, 4 on Wednesday, and today we're going to finish the final 4. Just kind of review what are the basic concepts that are involved. And then please remember to turn in your design projects today. Today is the last day of the semester, so I wish you all the very best in your exams. My understanding is our exam is next Friday, the last day of class. Is that correct?
Yeah.
Yes. Question? Yes.
Do you have any preference over paper or online?
I prefer paper, but if you put it online, it's not going to bother me. I can figure it out. Okay. My goal will be to spend the weekend grading, and I will try to have the exams graded by early next week in time for you to make a decision about how you want to perform on the final exam. I'll also send out a survey. It's an anonymous survey, and the survey will simply be asking you, whether or not you think you will be taking the final. The only reason I do the survey is, we have a class of about 46 people, but usually maybe only half of the people take it, or sometimes less. I mean, I've had as few as 5 people take it. And so I don't want to run off 46 copies of the exams if I don't need to. So the purpose of the survey will be simply for me to get a rough idea of how many people are going to show up on Friday morning. Okay, so please answer that survey when it comes out and say, yeah, I think I will or I think I won't. It's not a firm commitment. If you change your mind, it's not going to matter because I'll have a few extra ones. I just don't want to run 46 copies if I could have done, roughly 20. All right. I do intend to be around all week. Next week I've got a lot of other classes that have exams and stuff, so I should be in. If you have any questions about course material, I'll be happy to answer them in my office. All right, so let's work on the last few problems from spring of 2019. So the last few problems have to deal with frequency response design. So there's one here about frequency response design for a phase lag, and then we're going to take a look at a phase lead. There was a problem about root locus analysis. Okay, that was the other technique that we use for designing systems. Okay, so we have frequency response techniques. And then the last problem will be or was in the spring, it was a root locus design problem. And so we're going to take a look at these 4 problems this morning. Okay, so the first problem is going to be, or was a frequency response design. So the principle is that we're trying to change the characteristics of the control system. And one of the blocks is unknown. It's to be designed. We don't know what is this block. We know its structure. And the frequency response is given for this box, and we are trying to design the system to have certain characteristics. And so we consider that system, and the Bode diagrams are given for just this box. And so the Bode diagrams we realize are magnitude versus frequency. Frequency is labeled down here. And also phase versus frequency. And so this problem says the design parameters of this compensator. There's 3 parameters: K, S, and P. K, Z, and P. K, P, and Z to yield a control system with certain characteristics. And a couple specifications are given. One of them is that the steady state error has to be less than 0.05, 5%. And then we want to have also a 55 degree phase margin. So those are the 2 specifications. And so one has to understand basically on this graph, on these graphs, what do these specifications mean? And so when we talk about steady state error, we need to take a look at the low frequency characteristics. And so at low frequency, the low frequency gain affects steady state specification. Steady state means low frequency. So we had to study what's going on at low frequency. And so in this particular case, we're told that we want the steady state error to be less than 5%. And so what's not specified is if this is a steady state error for a step input or ramp input. But by looking at this thing, looking at the slope here, we can see that this is a type 0 system. This is type 0 because the slope is flat. And so it can only follow a step input, and it will have finite error. And the error will be 1 over 1 plus the position error coefficient. The position error coefficient, 1 plus 1 over the 1 position error coefficient has to be less than 0.05. And so we can solve for Kp. But Kp, the position error coefficient, is going to be the limit as s goes to 0 for this system is going to be the limit as s goes to 0 of Cg of s. Okay, so we have to take a look at the DC gain around the loop. And this particular system, we see that this part here, if we take the limit as s goes to 0, if we go to low frequency, s goes to 0, omega goes to 0, we see that we have a gain of 20 dB. And so this has a gain of 10. Okay, so this is a gain. This comes from the idea that it's 20 dB. But we want this number to be less than 0.05. Now Kp needs to be, at least maybe something like 20. So that means we need the DC gain, C at 0, needs to be equal to 2, at least 2, okay, greater than 2. Okay, everybody see how that comes about? We're trying to determine how much DC gain we need to get from the compensator, right? And we're seeing that the plant has some gain, we need some gain from the compensator. So if we take a look at the compensator and we look at what will happen when s goes to 0, when s goes to 0 here at DC, when omega is equal to 0, what we're going to get is that this term and this term drop out. This term and drop out. So C at 0 is just equal to K. So that means this K, if we want Kp to be equal to 20 and C0 has to be equal to 2, that means K needs to be equal to 2. So that parameter is designed in that fashion. Okay, so we're basically looking at the steady state error, low frequency behavior, and we determine what that gain needs to be. So if we add a gain K equal to 2, what's going to happen is that we need to know what happens to these plots here. We need to understand that the phase plot is not going to change because we have not added a 0 or pole yet. And so all that's going to happen is that this curve is going to be shifted up. And so we need to shift it up by the gain that corresponds to the gain of 2, and that corresponds to 6 dB. Okay, now, your work may differ from somebody else. Somebody could choose a different gain. As long as the gain at least greater than 2, it will meet the specification. Somebody else might say K equal to 10, in which case they've got to raise the curve by 20 dB. But let's suppose today I want to raise it 6 dB. And so looking at the scale here, 6 dB looks something like maybe about this much. And so I've got to raise the curve a little bit. I need to raise it 6 dB. And that's what's happened. Okay, so now that's the new gain curve because I've introduced a gain of K equal to 2. Now what we would like, however, is to have a phase margin of 55 degrees. And in this particular case, we can do it with a lag compensator. But the lag compensator cannot increase the margin. In other words, I don't add any, I cannot reshape this curve upward It cannot increase the phase curve. It can only drag the phase curve down. So we want to make sure that the phase lagging characteristic is at a frequency range which is not going to mess up our phase margin measurement. And so what we're going to do is we're going to seek a phase margin of 55 degrees, which means that the phase needs to be somewhat on the order of, say, 125 degrees, because 125 and 55 adds up to 180 degrees. So this is the dashed line minus 180 degrees. So let's take a look and see where 125 degrees comes in. And then we see that it looks like it's coming in right about here. So this is where we should be making our design. And that corresponds to a frequency of, we'll call that omega 0 equal to 2. This is 1, this is 10, so this is 2. So what we get here is that the desired phase margin could occur at omega equal to 2. Okay, and so we would get a 55 a 55 degree margin here. So in order to design the lag compensator properly, we need to make sure that the phase lag does not hurt us in this region. And so what we do is we pick Z to be a decade below that number. So Z is equal to 0.2 radians per second. Okay, so we just go a decade below, and so that puts Z right about here. Like so. The pole has to be chosen. We had to choose the pole. Choose the pole to remove excess gain. And the excess gain is going to be measured at omega 0. So we come here, we'll go to omega 0 equal to 2. We'll come up here, and we take a look at the gain, and the gain is right here. This is when we added that gain of K, we've increased things by 6 dB. And we want the phase margin to be at this frequency. That means the gain curve needs to go through this point right here. But right now it doesn't go through that point. We have too much gain. This is the excess gain. And so that has to be removed by the effect of the pole and the 0. And that looks like something on the order of maybe 12 dB. Okay, so the excess gain is approximately 12 dB. And so what we have to do is convert that out of dB, and that's, I can't figure that out in my head, but you have to figure that out in your head, I mean on your calculator. You said it's 25?
Yeah.
No, let's see, 20 dB is 10. 6 dB is 2. Yeah, 6 dB is 2. That's probably about 4. I think it's 4. All right. So then what we do is then P is going to be Z divided by 4, if I've done this calculation in my head correctly. Okay, so that kind of wraps up that problem. Okay, so the principle here is understanding that the phase lag compensator can increase the gain at low frequency, but also decrease the gain at high frequency. It introduces additional phase lag. It's going to drag the phase down, but we want to make sure that we stay away from where we're making this measurement. And so we do that by making the 0 significantly less than the pole. It was requested that these notes be scanned, and so I'll do that after class today. I'll add them to the other pages that we did on Monday and Wednesday, and I'll post them on Canvas. Okay, let's take a look at a phase lead design. Okay, so it's a very similar type of problem. In fact, if I look at these two graphs, it looks like they're identical. It's an identical block diagram, identical graphs, but the specification is just different. And let's take a look at the specifications. It says that we want to have a 60-degree phase margin, and a gain crossover of 4 radians per second. And a gain crossover of 4 radians per second. This is now a high frequency specification. Gain crossover is a high frequency spec. The previous problem talked about steady state error. That's a low frequency spec. That's a tip-off that maybe we want to use a lag type of compensator to improve the low frequency specification. Here we're given high frequency specification, so possibly a phase lead will be suitable. In fact, I tell you that it needs to be a phase lead. So I come in here to omega equal to 4. Let's find omega equal to 4. This is magnitude versus frequency. Magnitude versus frequency, this is 1, 2, 3, 4 right there. This is omega equal to 4. And we want the new curve to pass through 0 dB right here. So we want to go through that point. And at this frequency, we would like a phase margin of 60 degrees. So a phase margin of 60 degrees means that the phase curve needs to go through about 120 degrees, which I'm going to say is right about there. Okay, so we're going to call that minus 120 degrees. We would like the new phase curve to kind of go through that point and yield us a 60 degree margin, 60 degree phase margin. We have a little bit of margin, but we don't have quite enough. And so this little bit of phase, this phase here needs to come from the compensator. So we need phase lead. Okay, and so eyeballing that, I'm going to say that's probably about maybe 30 degrees. And so what we need, we say at omega equal to 4, we have two things that we need. We need a gain increase. The gain increase we need is something on the order of about 5 dB, 4 or 5 dB. And we need a phase increase. We need a phase increase. Let's call that theta m equal to about 30 degrees. Okay. So with these two pieces of information, then we can calculate the separation of the pole and 0. And so alpha is equal to the ratio of the pole over the 0. We can calculate that alpha needs to be equal to 1 plus sine of the amount of phase that we want to get from the compensator, 1 minus the sine, and we can get some sort of number. So that tells us what the ratio needs to be. So that's one equation, two unknowns. The second thing we need to know is we need to know where to put the pole and 0. And so the pole and 0 need to be straddling. They need to be straddling omega equal to 4. So the pole needs to be somewhere out here, and the 0 needs to be somewhere here. And they're evenly spread around 4. They're evenly spread geometrically. But of course, this is a log scale, and so it's not an arithmetic average, but it's a geometric average. And so the other equation that we have is that we're going to put the peak phase of the compensator halfway between the pole and the 0, like this. And so we're setting omega m equal to 4. So we say 4 is equal to square root of p times z. So we have two equations. We have this equation, and we have this equation. And so from these two equations and two unknowns, we can determine what are the pole and 0. Now we need to adjust the gain. The gain increase needs to be 4 or 5 dB. And so the gain increase is 4 to 5 dB. It comes from two parts. It's going to come from the gain of the compensator, K. We're going to express that in dB. Plus, the pole and 0 also add some gain. And so the amount of gain that they add is 10 times log of alpha. And so we calculated alpha before, so we know what this number is. So this is known. This is known, so we just have to solve for the gain k in dB and then convert out of dB. So we find k and then convert out of dB. Okay. So this this problem is a little bit more complicated in the sense that we have both the gain is going to increase because we're adding in a 0 and a pole, so that's going to increase this. But we're also adding in the phase. The phase is going to add 30 degrees. And so this is the phase of the compensator we're adding in, and this is the gain of the compensator that we're adding in. And so all the work is done right in the region where we're making stability measurements. And so conceptually, it's a little bit more difficult to sort everything out. But there are systematic methods, as we're demonstrating here, for designing the phase lead. Okay, let me pause to see if there's any questions about the phase lead. Okay. The next problem was dealing with root locus analysis. And so this is the other classical way of designing control systems, is that we can predict how the control system is going to behave if we have information about the open loop. And in this case, the open loop is only G of S. And so again, in all of the techniques that we're dealing with here, the Bode plot, the Nyquist plot, the root locus plot, the idea is that from open loop, we can predict closed loop behavior. Okay, that's the concept that is being examined here, and this is why on the design project I keep on asking, well, what model did you use for doing your Nyquist plot? What model did you use for doing your root locus plot? What model did you use for finding margins? And I'm looking for answers to always come back to the open loop. Okay. All right. So it says for each case below. So we have two cases here. We want to sketch the root locus diagram and analyze the stability of the control system for k greater than 0. And so here we take a look at the system. And one of the things that we have to remember about root locus concept is that the root locus plots the roots of the characteristic. It plots the roots of the characteristic equation. And the characteristic equation has to look something of this form. If we take a look at this system, if we plug this into here, what we're going to get is that it's going to be something like this. It's going to be 1 plus k s minus 1 over s plus 1, s plus 2, s plus 3 set equal to 0. And it's important to note is that this k is out in front. K is out in front. All right. And so we learned a few techniques for sketching the root locus, but one of the key assumptions is that the characteristic equation has this form where it's 1 plus k times some sort of function, and this k here must be in front. All right. Let me come down to this problem, and you see the k's in the bottom. And so when we take a look at the characteristic equation, it's going to be 1 plus 1 over k s squared plus 4 over s plus 2 s plus 3 equal to 0. And so this is not in standard form. This is not in standard form. So the rules that we use for drawing the root locus diagram cannot be applied directly. Normally we would just feed MATLAB, or we would feed our brain this model, and we would sketch the root locus diagram using these poles and zeros. And so to get started, say with this problem, I would construct my axes, label it real, and imaginary, and I start plotting the poles and zeros of this function, the open loop poles and zeros. And so that I have a 0 right here at +1, and then I have a pole at -1, a pole at -2, and a pole at -3. And this is how I get started. But I cannot do that here. I cannot do that here. I cannot take this function and start plotting the poles and zeros because k is not out in front like this. I have 1 over k out in front. So I have to do a little bit of work. This is not in standard form yet. And so we have to do a little bit of algebra. Okay, we have to do a bit of algebra. And so the algebra that we have to do is, let me first multiply both sides by this bottom part. And so I have k s plus 2 s plus 3 plus s squared plus 4 is equal to 0. Okay. And now you see that I have 2 groups of terms. I have a group of terms that are multiplied by k. They have k on front. Those are good. And these are other terms. Not multiplied by k. So group everything into, do a little bit of algebra, separate them into 2 groups. And now what we do is we're going to divide through both sides by this. We divide both sides by s squared plus 4. If I divide both sides by s squared plus 4, then I get k s plus 2 s plus 3 over s squared plus 4 plus 1 is equal to 0. Now this equation is in standard form because it looks like the form 1 plus k times something. Okay, so now this is 1 plus k times s plus 2 s plus 3 over s squared plus 4. And so now this is in standard form. Okay? And so now I would use this function to plot the root locus. I don't use this function. I need to use this function. And so if I were to plot the root locus diagram for this particular problem, I would come up here and say that I've got zeros at -2 and -3 and a pair of poles at plus and minus j2. And so I would have this 2 and -2. So we have to now then be familiar with the basic rules for sketching the root locus diagram. And the easy ones to do, let's first do the real axis. And so there's loci here and here. In this picture here, there would be loci here. Okay. We have a rule that tells us that loci start at the x marks and end on the o's. Or they go off the page. So here I have 2 x's, I have 2 o's, so the loci end on the zeros. The picture needs to be symmetrical, so a possible diagram would look something like this. Okay? And that would be a reasonable diagram to sketch for this problem. This particular problem, I have 3 poles, and I have 1 0. So I have 3 poles, 1 0. So the difference is 2, so that I have relative degree is 2. So that means I have 2 asymptotes. And the asymptotes are going to be a pair of lines, vertical, up and down like this. And I have to calculate where this is located. And this is going to be equal to the sum of the poles minus the sum of the zeros divided by the number of asymptotes, which is equal to 2 in this case. So I have -3, -2, -1, that's -6. -6 minus a +1 is negative 5 divided by 2, so negative 2.5. So I've got a set of asymptotes right about here. So probably this thing will look like, if I've done my math right, 6, I think I've done my math right, it might look like this. Okay. So this is just a little bit of root locus analysis, just drawing the diagram. The next question, it says sketch the root locus diagram and then analyze stability of the control system for k greater than 0. So in this particular case, we see that these loci lie entirely in the left half plane, but this locus here moves as k increases from the left over to the right. And so this system becomes unstable for large k. Okay. This system, the loci are all lying in the left half plane, and so this is stable for all k greater than 0. Okay. So the concepts here are understanding what is the root locus. The root locus is a diagram that shows the poles of the characteristic equation of the system. The system characteristic equation must have k out in front. If not, we have to do a little bit of algebra so that k is out in front. Okay, k is out in front. K is out in front. That's a key idea. We need to know how to sketch the diagrams. That's some basic idea there. And then we need to know what do these diagrams mean. What do the X's and O's mean? They're the open loop poles and zeros. What do the curves mean? They are the closed loop poles. And then so we can make some analysis of what the control system, the closed loop, is doing as gain k increases. A lot of work for 4 points. Okay. All right, the last problem last spring was a root locus design problem. And so we're given, we want, again, to design a control system that has certain characteristics. We're given a model of this box. We're given a structure for this box. We have a couple unknowns. This is design parameters k and z to yield a closed loop pole at this location. And then sketch the root locus diagram for the compensated system. And so what we have is we have to do a couple things. We have two unknowns, but root locus design gives us two equations to work with. And so the first thing we do is we apply the angle criterion. And the angle criterion basically says that the angle of C times G evaluated at this number, has to be equal to plus or minus 180 degrees. Okay. So if we take a look at the angle of these functions, the k and the 4 don't matter. And so what we have is that the angle of S star plus Z, this angle, and the angle of these bottom terms minus, this is the angle of S star, that's this term, plus the angle of S star plus 6, that's this factor. Got to do it twice because it's squared. That has to equal to 180 degrees. So geometrically, if we were to sketch this, we would get a picture that looks something like this. This is the real axis. Here's the imaginary axis. We have a couple of poles at -6. We have a pole at the origin. That's from the S term. We have a 0. We don't know where it is. I'm just going to just stick it out here. It's at -z. See, it's S plus z, so the pole's at -z. And what we're trying to do is we're trying to get the root locus to pass through this point here, S star, which is -3 plus J3. So it's -3
plus J3. This is S star.
Okay?
So what we're doing is we're drawing these lines here, 2 lines there, and we're saying that the angle to S star plus Z, this angle, I don't know what this angle is. It's an angle to a 0. The difference between it and the angles to the poles, this is the angle to S star, and this is the angle to S star plus 6. We'll do it twice, okay? All that has to be equal to plus or minus 180 degrees. And so this is known, this is known, this is known, and this is the only unknown. And so now it becomes just a trigonometry problem. We're going to end up finding out a number for this angle, and then we have to do a little bit of trick to figure out where this is. And so the picture in our mind is something like this. We have some point out in space called -3 plus J3. Here's the real axis, and we're going to get some angle called the angle. This thing is going to be solved for from this equation. This is going to become a known number. So we'll know this angle, but we're trying to figure out what is this number, and this is on the real axis here. So this becomes now an analytic geometry problem. Okay, so we have to solve for that. It's a geometry problem. Once that is solved, then what we do next is we apply the magnitude criterion to find the gain K. Okay, we need to find gain K. And the magnitude criterion tells us that K is equal to 1 over the magnitude of C times G evaluated at the closed loop pole. And so we just take the form that we have, and so what we have is we have to evaluate this thing on our calculator. We have S star plus Z, its magnitude, multiplying 4 divided by the magnitude of S star, multiplying the magnitude of S star plus 6 squared. Okay, so this comes from the plant. This comes from the compensator. Important thing is don't forget this. Okay, that's an easy thing to forget. There was a gain in the plant, and we have to know that. So Z has been solved for earlier in the earlier steps. So S star plus Z is known. S star is known. S star plus 6 is known. All this can be calculated. We have to remember to do the 1 over. Okay. And then we can solve for K. Simple problems like this can also be done by geometry, as some have shown on the last exam. But that's an example of a root locus design problem. Okay, any questions? All right. Then what we'll do is, that closes me out for the semester. I'll add these to the problems we covered on Monday and Wednesday, scan them, post them to Canvas. Wish you all the best of luck, and let you all turn in your design reports, and I'll start working on grading those.